Welcome to Complexity Made Simple. And in this video newsletter, what we're going to talk about, we're going to have a look at a case study, and it's all about how to make money with a DOE. So lots of DOEs, of course, are about process knowledge, but it isn't just about agreeing with the computer. It's about using your wisdom. The DOE just produces knowledge. What we want you to do is to take that knowledge, use it to the best of your ability, and make money. So we're going to make money with a DOE. Too many times what DOEs are about is maybe solving a problem, and that's fine. If you don't know how to make your machine land in a particular place, you don't know how to make your process land in a particular place, that's a great use for the design of experiment. But when you're trying to make the process land in the right place, it could be a very expensive solution that the computer comes up with, and we're going to let the computer come up with a solution in this little case study, but we're also going to use our wisdom and come up with better settings. Settings that please the customer, but settings that make more money. So it's a brand new machine. We don't have standard settings yet. We've set the machine up and created 30 pieces, hands off. And then what we're going to do, in order to optimize the process, we're going to conduct a designed experiment. So we're going to take a look. We're going to take a look at that case study right now. So here we are. It says that it's bore polishing. All right. So I haven't got a picture of the machine. I've taken some of the information out of this case study just so that the client is happy with a public presentation. But it's bore polishing, and what we're doing is we are replacing a manual process, which is very physical. It's quite hard on the operator. So the operators are getting problems with their hands and their shoulders doing this. So we want to put a machine in place and hopefully, of course, get a nice consistent performance, but also obviously make it faster, make more money, etc., and take away the physical aspect of the task going on. So it's a brand new machine. Bore polishing. So literally they've bought this machine, they've engineered a process, they've set it up, and then they've just produced 30 pieces with a guess of a setup, and we'll see what happens. So they produced this result here, which of course is very good. I mean, this is surface finish, by the way. So this is a surface finish result. Here's the top tolerance up here. You can see we're miles away from the top tolerance. This is a bit of a flyer, bit of a strange result there that we need to watch out for. But pretty much, look, everything's down here, well away from the top tolerance. The bottom tolerance, by the way, doesn't exist. That's 0. That would be like a mirror finish with no surface deviations whatsoever. So that would be perfection on the bottom. It's not a bottom tolerance. So there's the performance. Now we've just set it up. Now we could just put this machine into service and go, there you go. It works. There's our settings. But for just 50 pieces, that's all we're going to do. You know, a sample size of 50 pieces at the beginning of this. Why don't we see if there's better settings? So that's what we're going to do, and we're going to run a design of experiments in order to find that out. So there's the current performance. There's the capability. Remember that this bottom tolerance doesn't exist because this is actually 0. So we're sitting quite low. This, by the way, includes the flyer in the CPK analysis. This second one, look, doesn't include the flyer. So I would probably go with that one. That's a better representation of the true estimate of what's about to happen. So there's the current performance, but it's got particular settings. So they recorded the settings. Roll speed of 800, oscillation speed top roll pressure, cycle time, 35 seconds, for example. So there are the settings that created the result. So we're going to identify several of these variables to adjust, to test, and then we're going to see if there's a better setting or indeed there is a cheaper setting. So let's take a look at the DOE that was run. So the 4 variables that were run: oscillation speed, roll speed, cycle time, stone type. We collected data for surface finish. Let's have a look. 16 runs times 3. 48 pieces. So this is 48 pieces for what is going to produce thousands and thousands of parts a week. So this is very, very valuable. It's a very valuable 48 pieces we're about to come up with here. And then they also wanted to check stock removal. Now this process is a polishing process. It's not really supposed to remove stock. And if it did remove stock, that would be a problem, because the dimension has been set on a previous machine. We don't really want to change the dimension by polishing it. So stock removal is important to check as well. So we're checking surface finish, we're checking stock removal. Remember, the upper tolerance was 4 on the surface finish. So that's the area that we want to avoid, if you like. We want to be as close to 0 as possible, minimum as low as possible. So there's the 2 data sets. And then what we've got is the regression table that creates the models. Let's zoom in here a little bit. Here we go. Here's the regression table. So you can see lots of red p-values. That means we've got lots of influential variables. All 4 levers there were influential. 3-way interactions are influential. And the 4-way interaction is influential as well. 0.95 on the R-squared. So it's a very strong relationship between the inputs and the output there, the surface finish. 0.83 there for stock removal. So there are some things that are affecting stock removal. So that might be a little bit concerning when we get into the optimization. So there's the model. It's very strong. It's a great result to see in your DOE when you're seeing such good R-squareds, nice low p-values in your hypothesis tests. But let's go to the DOE Pro software now and see if we can do some process optimization and see what it tells us to set the machine to. So here we are, we're in Excel now, and we got DOE Pro running. What I'm going to do is go Graphs, Multiple Response Optimizer. So I'm going to go into the optimizer. The one thing I've got to remove the continuous check mark for there is the stone type, because I can't have half a stone type. I can only have stone 1 or stone 2. All the others are continuous, so we can leave those check marks in place. Then we can click on. Then I get this window up here to tell it the objective. Now the objective for surface finish, as defined by RA, is minimize the surface finish. And now add the objective. Now I don't really have an objective for stock removal, and I'm not going to say minimize stock removal and minimize the surface finish, because that's going to confuse the hell out of the computer. So actually I'm just going to leave it like that. I'm going to minimize the surface finish and I'm going to see what it does to stock removal. So I'm just going to say optimize, and then I'm going to go settings to worksheet. So now what I have in the yellow fields there, I have my 4 recommended settings. I have a prediction of 0.75, which is actually slightly better than what's currently being achieved with the other settings. But if you look at what we've got here. We've got the slowest cycle time. Now you might expect this. If we take longer to polish the surface, we're probably going to get a smoother finish. That would probably be expected. But everything's at the max effectively. We got oscillation speed at the max, roll speed at the max. We got cycle time at the max. So the computer has just maxed everything out. Now, of course, what that means is high energy consumption, slow cycle time. It's doing the job, but it's going to cost us more money than that original setting that we looked at. So that's not great. So what I'm going to do is use my wisdom, and I'm going to go, well, look, I'm well away from the top tolerance here. 0.75 is a million miles away from 4. I got plenty of room to save some money. Now I'm going to start with the cycle time. Now I'm just going to wind the cycle time here down to the low. Now look at that. That's roughly where we are now. So if I take my cycle time from 35 seconds, that was my original cycle time, down to 20 seconds. So I'm saving about 40% on the cycle time. How about that? And it's costing me nothing in terms of quality. Then the other thing I'm not very keen about, even though in the original settings, roll speed was up at 800 in our original setup. What roll speed will do is it will consume the roll. It will wear the roll out faster. It's obviously using more energy as well. So this thing potentially is going to cost us money if we're up at 800. So I'm going to wind this to the low first of all. I'm going to go all the way to the bottom, 200. Now look, that does have an effect. It has a major effect on the surface finish now. By the way, look at the stock removal. The stock removal is effectively nothing. So, you know, we've got the surface finish. We've got no stock removal. We're just below the middle of the tolerance here, 149. Now it's up to the client here. Do they want a really good surface finish? You know, let's go back to 800, 0.89, which would be the same performance now, and the cycle time's faster. They could just stick at that. Or what they could do is come down on the roll speed. Now I went right to the bottom, 200. Let's play tunes with this. Let's go to 400. You know, 129. So that's half speed from 800. Half speed. You know, and maybe that's the place that you want to go. But the point is, the client can choose, the engineer can choose. And this is the point about the DOE. We have so much knowledge here, we can play tunes with this. Now the oscillation speed, same thing, there's energy involved there, that's going to cost money. Let's see what happens if I wind that down. I'm going to go to 300 on that, see what we get. Now let me do that again. Let's put it back to 500. Yeah, it goes up a tiny amount, doesn't it? You know, let's go down to 100 on the oscillation. See, the oscillation's hardly doing anything at all. So we could stick here, look. We could stick here, oscillation speed down to 100, roll speed at 400, cycle time at 20, and we're using stone type 1. And that would get us 145 on the surface finish. You know, with the cycle times right up, we're not causing any quality problems. Obviously, what the engineer would have to do, what this client would have to do, is prove this out. One of the things that's missing, by the way, from this presentation, and I've got to be honest, I didn't really think about this until I've just made this presentation. I probably would have took 30 results from the hand polisher. So we would have seen what the hand polishing RA value was. And obviously, if we're inside that, if we're much better than that, and we're at the fastest cycle time we can get, we are really in the pound seats there. But this is the difference between process knowledge. Process knowledge is that model on the left-hand side. It's all those red p-values and those coefficients. That's process knowledge. But what we're applying is wisdom. The computer doesn't know how expensive those yellow values can be. Whereas we do know how expensive they are, and we can pick better settings. We can add our wisdom and make more money. The design of experiment software isn't very good at that, whereas we are. And that's where the two of you, the software, the process knowledge, and the wisdom, really make piles of cash. Put your wisdom with your process knowledge. Okay, now there's the case study. Now that really makes the point. DOEs aren't about running the DOE, run the maths, believe the computer. What a DOE is about is real, genuine, evaluated and quantified process knowledge. In that model we had there, it tells you what the coefficient is. That coefficient is in the unit of whatever you were measuring. Therefore, when I wind the 800 down to 200 and it moves, it tells me what it does to the surface finish. And I can decide, I know how much that's going to cost me or how much money it's going to make me, but I also know what it's going to do to the quality of the product. And then I can balance the two off and I can make a fantastically wise decision. Process knowledge and process wisdom. You put the two together, do a DOE, get the process knowledge, use good practical process wisdom. You put the two together, and what are you going to do? You are going to make bucket loads of cash. And now we can set that machine up to the best. We can be running 40% faster than the original test. We're well inside the tolerance. I don't know, what more do you want? And by the way, it took 50 pieces. That DOE took about 3 hours to run. It's the fastest way to get the most knowledge and make the most money. Surely you'd want to do a DOE when you get a new machine and make more money.